Good morning, everyone. Myself, SJBIT, Assistant Professor, Department of ACE, SJBIT. The subject that I am discussing about is digital communication. The subject code is 18AC61. We are discussing about the Module 5 topics. The Module 5 includes spread spectrum communication systems, in which first we need to discuss about the model of spread spectrum digital communication system, direct sequence spread spectrum systems, effect of despreading on a narrowband interference, probability of error, which we need to consider only the statement, some applications of DS spread spectrum signals, generation of PN sequences, frequency hopped spread spectrum, and finally CDMA based on IS-95. First, let us discuss about the introduction to spread spectrum. There are some applications like military communication, in which when we transmit the message, that message has to be received only by the receiver, because in the military communication the information has to be sent to the receiver, only to the receiver, and it should not be received by any other users. And in order to make the communication reliable, others should not be able to jam the transmitted signal. In order to deal with this, the spread spectrum systems are intended to provide such a secure and reliable communication. As the name tells, these systems spread the spectrum of the transmitted signal over a very wide bandwidth, and this is achieved in these systems by modulating for a second time an already modulated signal in such a way as to spread the power of the transmitted spread spectrum signal over a very large bandwidth. Hence, the power spectral density of these signals is very low that any ordinary AM or FM receiver with its 10 kHz or 200 kHz front-end bandwidth will receive an amount of spread spectrum signal power which is very much lower than the thermal noise power which is entered the receiver. As a result, the unauthorized receiver will not be able to receive the spread spectrum signal. The spread spectrum signal cannot easily be jammed, hence it is very secure as well as reliable communication is possible, which is mainly required in military communications. And one more advantage of spread spectrum signal is that it enables an increase in the number of users over a given band. And this is a feature that is mainly exploited for providing multiple access in satellite communications. As well, in cellular mobile communications, in order to go for increase in the number of subscribers using the same band, this spread spectrum signal can be used. Now, let us discuss briefly the advantages of this spread spectrum's communication. It mainly provides the protection against eavesdropping, means whenever any intruder wants to interfere the signal that is being transmitted, if you want to just, it is providing the resistance to intentional jamming as well. And whenever there is a fading in the signal which is caused by multipath effects, that fading can be resisted by means of this spread spectrum communication. And as we discussed, the multi-user facility over a given channel is provided by means of this, as well as the ranging facility is one more important advantage that we get from this spread spectrum communication. Now let us start with this spread spectrum communication. First thing that we need to know here is, what is spread spectrum? What is the definition of spread spectrum? We can define this spread spectrum in two parts. It is a measure of transmission in which the data of interest, it occupies a bandwidth which is in excess of minimum bandwidth necessary to send. And the spreading of the spectrum is accomplished before the transmission through the use of code which is independent of the data sequence. And the same code can be used in the receiver in order to despread the received signal so that we can recover the original data properly. These two parts can be together called as the definition of the spread spectrum. Now let us discuss the principles of spread spectrum modulation, considering the types of spread spectrum like direct sequence and frequency hopping technique. This is a model of the spread spectrum digital communication system. In this model, as you can see, this model is of basic digital communication system with some additional blocks that make up the spread spectrum communication system. Those additional blocks are pseudo-random pattern generator used at the transmitter as well as at the receiver. As we know, first the information sequence will be sent to the channel encoder. From the channel encoder, it is being sent to the modulator. The modulator modulates the signal. In this modulator itself, the pseudo-random pattern generator will be given as one more input to the modulator. The output of the modulator will be given to the channel, which may be wired or wireless channel. The output of the channel will be given to the demodulator, and one more input to the demodulator will be pseudo-random pattern generator. The output of the demodulator is given to the channel decoder, and finally from the channel decoder we get the output data. As we know, in the conventional digital communication system, the channel encoder and decoder and the modulator and demodulator can be considered as the basic elements of the digital communication system. And in spread spectrum digital communication system, as I mentioned, it uses pseudo-random sequence generators at the transmitter and the receiver. And these pseudo-random sequence generators that are used at the transmitter and the receiver, they should be identical one interfaces with the modulator at the transmitting end and another interfaces with the demodulator at the receiving end. These two pseudo-random sequence generators, they produce a pseudo-random or pseudo-noise binary valued sequence, which we call it as PN sequence. The pseudo-random sequence used at the transmitting part, it is used to spread the transmitting signal, and the pseudo-random pattern generator that is used at the receiving side, that is used to despread the received signal at the demodulator. And the time synchronization of the PN sequence is mainly achieved by transmitting a fixed PN bit pattern, and this will be designed so that the receiver will detect it with high probability even in the presence of the interference. Now, in the transmission of the spread spectrum signal through the channel, the interference will be introduced. This interference can be categorized as either broadband or narrowband interference, which is being related to the bandwidth of the information bearing signal, and it may be either continuous in time or discontinuous in time. And finally, when I tell digital modulation, two types of digital modulation will be considered. One is PSK, another one is FSK. Phase shift keying, frequency shift keying. The PN sequence which is generated at the modulator will be used in conjunction with the PSK modulation, and it will shift the phase of the PSK signal pseudo-randomly at a rate which is integer multiple of the bit rate. And in such a case, the modulated signal will be called as direct sequence spread spectrum signal. The PN sequence, when the PN sequence, it is used in conjunction with a binary or M-array PSK. It is used to select the frequency of the transmitted signal pseudo-randomly. In such a case, the resulting signal is called as frequency hopped spread spectrum signal. Whenever the PN sequence is used with PSK, it will shift the phase of the PSK signal pseudo-randomly at a rate which is an integer multiple of bit rate. In such a case, the resulting modulated signal is called direct sequence spread spectrum signal. And when the PN sequence is used with M-array FSK and the frequency of the transmitted signal is being selected pseudo-randomly, in such a case, the resulting signal is called frequency hopped spread spectrum signal. This is the waveform of direct sequence spread spectrum system. The first waveform is a PN signal waveform. The second is the data signal. The third is the product signal, which represents the direct sequence spread spectrum signal. The third signal, as the name tells, product signal. It is the product of the PN signal and the data signal. As you can see here, the value is been ranging from -1 to +1, -1 to +1 in all the three waveforms. The minimum value is -1, the maximum value is +1. Now in the first interval, the PN signal as value 1 as well as the data signal as value 1. So 1 into 1 will be 1 in the product signal. Coming to the second interval, next interval, the PN signal as value -1, the data signal as value +1. So -1 onto +1 will be -1 in the product signal. Similarly, moving on to the next interval, the PN signal has value +1, amplitude +1, the data signal as amplitude +1. So +1 into +1 will be +1 in the product signal. Next interval, the PN signal as value -1, the data signal as value +1. So -1 into my +1 will be -1. Next interval, PN signal +1, the data signal -1, +1 into -1 will be -1. Next interval, PN signal -1, data signal -1, -1 into -1 will be +1. Next interval, -1, this is -1 and this will be +1. Next interval, this is +1, this will be -1, +1 into -1 will be -1. Like this, the product signal is the multiplication of the amplitudes of the PN signal and the data signal. Now let us discuss about the mathematical equations governing the spread spectrum communication system, basically the direct sequence spread spectrum system. The basic method for accomplish the spreading we discussed in the figure, and the information bearing baseband signal is denoted as V of t, and it is being expressed as summation n is equal to -infinity to +infinity an gt of t minus ntb, where an is equal to ±1 as I discussed, n ranges from -infinity to +infinity, and gt of t is a rectangular pulse of duration tb. Let us take this as equation number 1. Now this signal, that is the information bearing signal, it will be multiplied by the signal from the PN sequence generator, which we call it as PN signal, and it can be expressed as, this PN signal can be expressed as C of t is equal to summation n is equal to -infinity to +infinity Cn P of t minus ntc. Here the sequence Cn represents the binary code sequence of ±1s, and P of t is a rectangular pulse of duration Tc, as we noticed in figure A. This multiplication operation of V of t into C of t, it is basically used to spread the bandwidth of the information bearing signal into a wider bandwidth, which is occupied by the PN generator, a signal C of t, and this spreaded signal we noticed in figure C, which is nothing but the product signal. Now let us see the spectrum spreading. The first figure represents the spectrum of the information bearing signal, which is represented as V of f. It is ranging from -1 by TB to +1 by TB. Second is the C of f, which is the spectrum of the PN signal, and it is ranging from -1 by TC to +1 by TC. And the third waveform is the spreaded signal, that is the product of V of f and C of f, which is represented as V of f into C of f. V of f into C of f represents the spreaded spectrum, which is having the range added together, the ranges of V of f and C of f on the positive as well as on the negative interval. On the positive interval we have minus of 1 by Tc plus 1 by Tb. On the negative interval, on the positive interval we have 1 by Tc plus 1 by Tb, which is a spreaded spectrum signal. This product signal V of t into C of t, it basically amplitude modulates the carrier AC cos of 2 pi fct, and it generates the double sideband suppressed carrier signal DSP-SC signal, and this is given by U of t is equal to AC V of t C of t cos of 2 pi fct, which we can call it as equation number 3. We know that when we multiply the amplitudes, the multiplication of amplitude will be resulting in either +1 or -1. It means V of t into C of t results in plus or minus 1 for any time t. So this equation can be expressed as U of t is equal to AC cos of 2 pi fct plus theta of t, where theta of t is equal to 0 when V of t C of t is equal to 1, and theta of t is equal to pi when V of t into C of t is equal to -1. It means this 0 and pi transitions in the phase representing what? It is representing a PSK signal for +1 as well as -1. Therefore, this transmitted signal is a binary PSK signal. Now moving on to the terminologies that we come across in the PN sequence. The rectangular pulse P of t, which is used to represent the PN sequence, we call it as a chip. And the time duration of this pulse P of t, we call it as chip interval Tc. The reciprocal of this Tc is called as chip rate, that is 1 by Tc. Now, the ratio of bit interval Tb to the chip interval Tc, we select to be an integer, and we denote this ratio as Tb by Tc is equal to Lc. Here Lc is nothing but the number of chips of the PN code sequence per information bit. Also, this Lc represents the number of possible 180-degree phase transitions in the transmitted signal during the bit interval Tb. Until now we discussed about the modulation of DS spread spectrum signal. Now let us know about the demodulation of direct sequence spread spectrum signal. In the demodulation, as we know, the input will be the received signal, which is represented as R of t. And as we have come across the digital communication system, basically for spread spectrum signal, the received signal R of t is multiplied with C of t, which is the signal coming from the PN signal generator used at the receiver section. The output will be given to the multiplier, which is having one more input as GT of t cos of 2 pi fct. The output of this will be given to the integrator, and finally to the sampler, which is sampled with respect to the clock signal, and finally the output will be given to the decoder. In this receiver block diagram, As I mentioned, the received signal is first multiplied by the waveform C of t, which is generated by the PN code sequence generator at the receiver, which is actually synchronized to the PN code in the received signal. This operation we call it as despreading operation. Finally, we have B of t equal to R of t into C of t. AC V of t C of t cos of 2 pi fct into C of t is the signal that we get after substitution. And finally, C of t into C of t results in C square of t. This C square of t will be 1 for all t, because C of t will be either plus 1 or minus 1. Finally, B of t will be, the dispreaded signal will be ACV of t cos of 2 pi fct. The received signal ACV of t cos of 2 pi fct, it occupies a bandwidth of R Hz. And this is the bandwidth of the information bearing signal. Hence, the demodulator for the disparate signal is simply the conventional cross correlator or the matched filter. Finally, we can conclude that the demodulator for the disparate signal is either a cross correlator or a matched filter.